Hello, everyone. Welcome to ILTA Physics. I'm so glad you could join me for today's online lecture. Today, we're going to study the momentum of an object in motion. Momentum can be defined as the intensity or the total amount of motion an object has, and it's sometimes referred to as the mass of motion. To use a rough analogy, similar to how we explain inertia as the equivalent of mass for rotating objects, you can think of momentum as the total quantity of motion a moving object possesses. To help you understand this more practically, momentum is often described as a measure of how difficult it is to stop a moving object. As you can see in the diagram on the right, if a baseball and a car traveling at the same speed hit a wall, the impact they deliver will be very different. From a kinematic perspective, two objects with the same velocity and direction represent the same type of motion. However, if the results of hitting a wall are different, doesn't that mean there's something different about the total amount or intensity of those two motions? The concept that allows us to describe motion more accurately in this way is precisely what we call momentum. To get a solid grasp of momentum in today's lecture, we're first going to derive the original version of Newton's second law, which most of you know as F equals ma. Through this relationship, we'll define the total quantity of motion a moving object has. In other words, we'll define momentum. Then we'll derive the impulse momentum theorem, which is one of the most important concepts when it comes to collisions. Finally, we'll wrap things up by looking at the relationships between the concepts we've covered today: momentum, impulse, and force. All right, let's start with a quick review of what we covered last time. Starting from our last lesson, our physical perspective has shifted. Previously, we analyzed the motion of objects from a kinematic perspective focusing on individual bodies. Now, we're moving on to interpreting how multiple objects behave when they interact with one another. Specifically, we want to describe the state of motion before and after an interaction. For example, before and after a collision. Let's look at the image below and think about a golf club hitting a golf ball. We call the very strong force applied to the ball over a very short period of time the impact force. As shown in the graph on the right, the impact force applied to the ball changes in a bell shape over the duration of the collision. Ultimately, the total force applied to the ball, which is the impulse, is equal to the area of the gray region on the graph. This can be expressed as the product of the average impact force and the duration of the collision. Now, let's use this concept of impulse to take a deeper look into the motion of objects. Let's recall Newton's second law, which has played the most vital role in how we analyze motion of an object. An external force applied to an object causes a change in its velocity, which is acceleration. This acceleration is proportional to the applied force and inversely proportional to the object's mass. If we express this as an equation, it looks like this. It's the formula we usually memorize as F equals ma. However, Newton actually explained that a change in an object's velocity is related not just to the force applied, but also to the time during which that force is applied, the impulse. As shown in the image on the right, the impulse applied to the golf ball creates the acceleration of the object. Newton explained this physical relationship from both a kinematic and a kinetic perspective. From a kinematic standpoint, acceleration is defined as the change in velocity divided by time interval. And from a kinetic standpoint, we know that an object's acceleration is proportional to the force and inversely proportional to the mass. Now let's reorganize the relationship between the last two terms of this equation. By using the rule that the cross product of two fractions is equal, we can rearrange the formula like this. The product of force and time is equal to the product of mass and the change in velocity. So far, does everything make sense? Have you been able to follow along well up to this point? Here, the left side. Force times time interval is the physical quantity we previously defined as impulse. Therefore, if we define the right side, mass times velocity change, as the momentum of a moving object, we can rewrite the equation as follows. In other words, the physical meaning of this relationship is that the impulse applied to an object results in a change in the object's momentum. If we rearrange this in terms of the force applied to the object, it looks like this. To put it another way, Newton's second law can be described like this. The external force applied is equal to the change in an object's momentum divided by the time interval. Of course, this means the same thing as F equals ma. But I want you to understand that this is a very important equation for interpreting the relationship between force and acceleration through the lens of impulse and momentum. Now, let's summarize the concept of momentum that I introduced briefly earlier. As Newton's second law states, the impulse applied to an object changes its momentum, meaning it changes the object's velocity. In linear motion, momentum is defined as the quantity of the motion a moving object possesses. In practical terms, it's also described as a measure of how easily you can bring a moving object to a stop. As we intuitively know, a heavy and fast-moving object is harder to stop than a small, slow-moving one. In other words, we can understand that it has more momentum. If we express this as a quantitative relationship, momentum can be calculated as the product of an object's mass and its velocity. For example, if a large truck and a small car are traveling at the same speed, the truck has more momentum because of its mass. On the other hand, if two baseballs with the same mass are flying at different speeds, the momentum formula tells us that the faster ball has more momentum. Now, in the next section, we'll take a look at the impulse momentum theorem and its applications. Let's recap the relationship between impulse and momentum one more time. This is the same relationship we looked at while explaining Newton's second law. If we describe acceleration from both kinematic and kinetic perspectives, it looks like this. And by rearranging it, we can conclude that the impulse applied to an object is equal to its change in momentum. If we write out the change in momentum as a formula, we can see it's the difference between the mass times the final velocity and the mass times the initial velocity. In the case of a constant impulse, you can either have a large force acting over a very short time, like hitting a ball with a bat, or you can increase the collision time to create a smaller force, like an airbag does. Let's look at the physics of an airbag in more detail. If a car hits an object head-on, an impulse is generated by that collision. This impulse has a set magnitude based on things like the car's weight and speed. The goal of an airbag is to transfer as little of that impulse as possible to the person inside. Let's say the blue arrow in the diagram below represents the force transferred to the person. According to the impulse momentum theorem we just discussed, force and collision time are inversely related. So, the inflated airbag increases the duration of the collision, which ultimately results in reducing the force delivered to the person. Your physics knowledge could literally save a life. That's why physics is so important, right? That's it for today's lecture. You all did a great job. I'll see you in the next class.